Okay, in the last video we introduced the concept of concavity, right? Concave upward, where the derivative is increasing. Concave downward, where the derivative is decreasing. And of course that gives us this test, right? If the derivative is increasing, the second derivative is positive, and therefore the function is concave upward, the second derivative is positive. If the second derivative is negative, that means the derivative f prime is decreasing, which means f is concave downward, as we have here. Okay, keep in mind, again, you can be concave upward decreasing, concave upward increasing. It could be concave downward increasing, concave downward decreasing. We'll get more into that in the next set of lectures. Also, we have points of inflection. How do we determine points of inflection down here at the bottom? We will define them where what? The second derivative is 0 or undefined. And important, we have a sign change in the second derivative, either from positive to negative or negative to positive. That will be a point of inflection. Okay, so how do we proceed given a basic function like this, which is nice, polynomial? First thing is just to remember what's the domain, because we are only talking about values of x in the domain of the function. Of course, this is a polynomial function, so the domain is all real numbers. All right, what do I need to do? What's my first step? At this point in the ball game, I'll give you a hint. If you're unsure what to do, take a derivative. Just take a derivative, right? So that's clearly what we're going to do. Take a derivative, and we're going to apply it. In fact, we're going to not just take the derivative, but we're going to take the second derivative. Let's get the first derivative here. Real easy, right? Hopefully everyone has no problems in finding the derivative of a polynomial function at this point. I think we're all good with that. Bring the 2 down, I get negative 24. Subtract 1 from 2, I get x. Derivative of constant 8 is 0. And then I want to look at the second derivative, because when I'm talking about concavity, that's what's important. So bring the 3 down, I get 12x squared minus 24. Now it is helpful because I'm going to be analyzing when the second derivative is basically positive or negative. To go ahead and factor this, I can factor out a 12. Right? And so there we have the second derivative. So the first thing is, when is this second derivative equal to 0? It's never undefined, right? Domain is all real numbers. But it's equal to 0 when what? When x squared minus 2 equals 0. Right? Obviously 12 can't be 0. So that's true when x squared is 2, or when x is what? Don't forget, positive or negative, the square root of 2. Okay? So what are we going to do? I want to know where the function is concave up or concave down in points of inflection. So we just said that depends on the sign, S-I-G-N, of the second derivative. So what do you think we need to do? We need to do a sign check of the second derivative. Remember, to find out where a function was increasing or decreasing, we were doing a sign check of the first derivative. To determine where we're concave up and concave down, we do a sign check of the second derivative. Let me put my 2 points of interest here where the second derivative is 0. Okay. And then, clearly I'm looking at the second derivative, which, is a parabola, isn't it? Graph is a parabola because it's quadratic. 12 is positive, so it's opening upward. I know what this graph looks like. It looks like that. Okay. And so it's going to be positive, negative, positive. But you can plug in values again in between and beyond and get the sign of the second derivative in each case. All right. So now we can answer the questions, right? Where is the function g concave? I'm going to abbreviate that. Concave up. It's concave up where what? The first derivative is increasing, which occurs when the second derivative is positive, right? So we're looking for when the second derivative is positive. Well, it's clearly going to be positive when the value of x is less than negative square root of 2, and also when it's greater than the square root of 2. G is concave down. So little ditto marks, right? Is concave down on the interval what? Well, we're concave down where the derivative is decreasing or the second derivative is negative. So on the interval from negative root 2 to root 2. And does G have any inflection points? I'll just say points of inflection. And here I'm just going to give the location. Okay, where do they occur in terms of the x value, the input value? Well, clearly we see, I mean, you can tell right from this, right? What happens? Concave up for values less than negative 2, and then we're concave down from negative square root of 2 rather to 2. So there's a change at negative square root of 2 in concavity. And then we change from concave down to concave up at the square root of 2. But in terms of the test, we see a sign change in the second derivative at both negative square root of 2 and positive square root of 2. It doesn't matter if you go from positive to negative or negative to positive. All we're looking for is a sign change. So at x equal plus or minus the square root of 2. Now if you really wanted to know what the points of inflection are, what would you do? How would you find the actual points of inflection? You would take the input negative square root of 2, for instance, for x, and what would you plug that into? The second derivative? No, because we know second derivative gives me 0. That's not what I'm interested in. Points of inflection on g, I plug it into the function g. So g of negative square root of 2. All right? And the other one would, of course, be square root of 2, comma, g. You want to actually find the point, right, the xy coordinates. But I'm typically interested in just give me the location. Okay. If you need to find the actual point, then you have to go back to the original function, plug into that to find the actual point. Okay? Let's do another example. Right off the bat, I'm going to write this function in a different form. We're going to be taking the derivative. A lot of you might say, oh, I'm going to use the quotient rule, which is fine. But I'm going to rewrite this as x squared plus 4 to what power? Negative 1. I'm going to end up using the chain rule here. The domain here is what? I'm dividing by something, so be careful. Can this denominator ever be 0? Is there any value of x that will make it 0? No. X squared is always greater than or equal to 0, and so x squared plus 4 is always 4 or more. So the domain is all real numbers again. I can plug anything in. Okay, so what is the derivative? It's negative x squared plus 4 to the negative 2. Right? That's the derivative of the outer function evaluated at the inner. So what am I talking about? What rule do I need to do here? I'm not done. Chain rule, right? Some of you are forgetting the chain rule. So be real careful. Times what? The derivative of what's inside, which is 2x. Right? So this is the chain rule. Make sure you're clear on that. And so cleaning this up a little bit, I get negative 2x. I'll pull that in front. X squared plus 4 to the negative 2. I'm going to leave it as negative 2 because I'm really wanting to get down to the second derivative. Okay? Now, what rule do I have to use on the second derivative? You say chain rule. Yeah, I've got a chain rule, but more importantly, what? I've got to do what? Product rule. So you can't forget that. There's a couple of you that kind of let that slip. Make sure you're clear. You have to take the derivative of one times the other, and then vice versa. So if I take the derivative, so let me just write this out. So negative 2x, take the derivative of that, plus the derivative of that. Now there's the chain rule in here, so the product rule. Right? And of course the derivative of negative 2x, that's easy, that's just negative 2. What's the derivative of this thing? Well, that's by chain rule, so negative 2 x squared plus 4 to the negative 3, subtract 1, right? And then times the derivative of what's inside, that's 2x. So if I clean this up a little bit, I get negative 2 x squared plus 4 to the negative 2 And then here, be careful, I've got negative 2x times a negative 2 is positive 4x times 2x. 4 times 2, 8, x times x, x squared. So this times that, and then I have this x squared plus 4 to the negative 3. Okay, there's my second derivative. Now, what I would like to do is factor this, just like I factored the last one. And what can I factor out of this? Well, negative 2 and 8, I'll factor out a negative 2. You could factor out a positive 2 if you want to, but I'll get rid of that negative in the front. And then there's an x squared here, but no x squared term here. There's an x squared plus 4 term for both. What do I factor out? X squared plus 4 to what power? Negative 2 or negative 3? What do we do? Remember, the smaller power is the best. Pull out negative 3. Okay, what's left? Pulled out the negative 2 from here. I pulled out x squared plus 4 to the negative 3. So what's left here? X squared plus 4 to what power? Remember, when we multiply these two together, what are we going to do with the exponents? We're going to add the exponents. Negative 3 plus something equals negative 2. What's the answer? Negative 3 plus 1 equals negative 2. So this is just x squared plus 4. Here I factored out a negative 2 from a positive 8. That leaves a negative 4. I've got my x squared still. This whole thing to the negative 3 power was pulled out. And so this stuff in here I can simplify inside the hard brackets. I've got 4x squared minus 4x squared is negative 3x squared. And now I'll go ahead and write q double prime of x is negative 2 times 4 minus 3x squared all over what? X squared plus 4 to the positive 3. So bring that down. Right. Negative exponent comes down here. All right. A lot of work there, but now it will pay off. What is the value of x that makes this second derivative 0? Well, that'll be when what? 4 minus 3x squared is 0. Or when 3x squared is 4. Or when x squared is 4/3. Or when x is what? Plus or minus square root of 4 is 2 over the square root of 3. I'll leave it like that. You know, some if you look, you might look in the back of the book and see there's what? Plus or minus 2 root 3 over 3. I'll just leave it as that, but you know, they've rationalized, that's fine. I'll just leave it like that. So what do I do now? I do my sign check. So I've got minus 2 divided by square root of 3 and plus 2 divided by square root of 3. Sine of q double prime is 0, both of those. Now look at this. We want to look at the sign of this whole thing, so don't forget, go back to this whole thing. So if I plug in something less than negative 2 divided by square root of 3, square root of 3 is about 1.7, so this is a little bit more than, a little bit less than negative 1. Let's just do negative 5. I don't know, negative 5. So if I plug in negative 5 here, I get negative 5 squared is 25. 3 times 25, 75. 4 minus 75, that's a negative number up top. A negative number, rather, in the parentheses. Times a negative 2. Negative times negative, so actually up top, positive. What about down here? Well, notice since I square x and then add 4, this is always positive. So positive divided by positive, positive. If I plug in 0, right, for x, the bottom is just 4 cubed. The top is negative 2 times 4, negative 8. Negative divided by positive is a negative. And then if I plug in something bigger than 2 divided by square root of 3, like positive 5, if I plug in positive 5 up here, again, I'll get a negative times a negative, which is positive, over the positive, back to positive again. All right, and then we can finally answer the question, right? Q is concave up on what intervals? Where the second derivative is what? Positive. Q is concave down when what? Second derivative is negative. So between these two values. And then Q has points of inflection at x equal what? Well, we change sign in the second derivative, right? All right, they're at plus or minus 2 over square root of 3. Okay. So this video had a couple of examples. I'm going to stop the video here now. The next video we'll do another example with a trig function, and then we'll close out with something known as the second derivative test, and that test goes back to finding local max and mins, another way other than the first derivative test which we looked at last time. So we'll do that in the last video here for this topic on concavity.